Section: Introduction. In this section, we discuss how recent improvements in reinforcement learning techniques have significantly enhanced the reasoning capabilities of large language models. Notable systems, such as OpenAI's models, now achieve or exceed human-level accuracy on various challenging tests. Among these, the open-source Qwen family, with sizes ranging from 0.5 billion to 72 billion parameters and trained on up to 36 trillion high-quality tokens, stands out for its performance in language understanding, mathematics, programming, and preference alignment. Mathematical reasoning has become a key area for testing these models, as it requires precise manipulation of symbols and multi-step logical thinking. Standard tests like Math 500 and others require models to interpret natural language problems, identify the underlying mathematical concepts, and produce accurate numerical answers. Recent advancements have improved these models through reinforcement learning with verifiable rewards, where a reward of 1 is given for a correct answer and 0 for an incorrect one. This method simplifies training by eliminating the need for a separate reward model, which is particularly beneficial in mathematics, where answers are clear-cut. Interestingly, we note that even random or partially incorrect rewards can enhance Qwen's performance on math tests, while similar methods do not benefit llama models. To explore why this is the case, we compare the two model families under the same training conditions. We propose two hypotheses. 1. Data contamination. Qwen may have been pre-trained on vast internet data, including benchmark problems and their solutions. If parts of the evaluation benchmarks were included in its training data, it could lead to the model recalling memorized answers instead of developing new reasoning skills. 2. Strong baseline math skills. Qwen's pre-training might give it a higher mathematical ability than llama, allowing it to perform better even with noisy updates. However, if strong skills are the main factor, the same random reward approach should work on a clean benchmark. To investigate these possibilities, we conduct a leakage audit and an out-of-distribution evaluation. We assess potential data contamination by looking at two indicators: the model's ability to complete problem statements and its accuracy in answering incomplete problems. Our findings show that Qwen can effectively complete and answer problems, while llama struggles significantly. However, when tested on a new benchmark created after Qwen's release, both models perform poorly, suggesting that earlier successes on Math 500 may be due to memorization rather than true reasoning. We conclude that data contamination is likely the main reason behind Qwen's unexpected success with random reward methods. To test this, we create a new benchmark with randomly generated arithmetic expressions, ensuring no overlap with Qwen's training data. A zero-shot evaluation reveals that Qwen's accuracy decreases as the complexity of the problems increases, indicating no memorization. Next, we train Qwen under standard protocols on two clean subsets and find that only correct rewards lead to consistent performance improvements. In contrast, random rewards result in unstable training with no reliable gains, while incorrect rewards harm the model's reasoning abilities. This rules out the strong skills hypothesis and supports the idea of data contamination. Once we eliminate leakage, previous performance gains disappear. In summary, we conduct a thorough audit of math benchmarks, showing that Qwen's performance increase on Math 500 is mainly due to unfair evaluation and memorization rather than superior math skills. We develop a generator for creating arithmetic problems and a new evaluation method, revealing that both Qwen and llama perform similarly when tested fairly. Our controlled experiments highlight the importance of using accurate rewards for stable performance. We recommend that future research utilize uncontaminated benchmarks to draw reliable conclusions about reinforcement learning methods. Section Summary. In this section, we analyze the performance of large language models, particularly the Qwen family, on mathematical reasoning benchmarks and identify data contamination as a key factor behind their apparent success. Our findings reveal that when evaluated on clean, leakage-free datasets, Qwen's performance aligns more closely with llama, emphasizing the importance of reward quality in reinforcement learning training. Section: Related works. In this section, we explore related works on reinforcement learning applied to the Quen 2.5 model for enhancing mathematical reasoning. We note that many studies have shown how reinforcement learning, RL, can improve the mathematical skills of Quen 2.5. Early research utilized clear rewards, scoring answers as either correct or incorrect based on exact numerical matches. During testing, RL applied this feedback in real time, leading to significant improvements on datasets like Math 500 and AMY 2024. Later studies aimed for high data efficiency, where even a single labeled example could enhance performance, and some methods learned from unlabeled data by minimizing uncertainty. We also observe approaches that replace external rewards with internal signals from the model itself. For instance, some methods reward low uncertainty outputs, while others rely on self-consistency for feedback. These strategies have led to substantial improvements on Quen 2.5 Math 7b, sometimes even exceeding stronger benchmarks. However, the general effectiveness of these methods has been questioned, as some researchers noted a pattern where accuracy initially increases but later declines as the model becomes overly confident. Additionally, it was found that random or incorrect rewards could still enhance Quen 2.5's performance but did not transfer well to other models, indicating that the effectiveness of RL is closely tied to reward design and the model's inherent capabilities. Next, we discuss the impact of pre-training data on reasoning abilities. The choice of pre-training datasets is crucial, especially in mathematics. Various math-specific datasets have been shown to significantly improve performance on relevant benchmarks. We highlight that models like Quen and Llama, despite being similar in size, show different capabilities in mathematical reasoning. For instance, Quen models tend to benefit more from reinforcement learning, while Llama models show limited improvement. Research has indicated that training Llama models on high-quality mathematical data can greatly enhance their performance, suggesting that the pre-training data significantly affects a model's responsiveness to reinforcement learning. In terms of model selection, we focus on 4 key checkpoints from the QWEN 2.5 family: Quen 2.5-7b, Quen 2.5-7b Instruct, Quen 2.5 Math 7b, and Quen 2.5 Math 7b Instruct. For comparison, we also evaluate Llama 3.1-8b and Llama 3.1-8b Instruct, which have similar parameter counts, allowing us to isolate model-specific differences. We then detail our evaluation of the model's memorization capability using 2 metrics: partial prompt completion rate and partial prompt answer accuracy. For the Rouge metric, we explain that Rouge is a set of metrics used to assess automatic summarization and text generation. It measures how much the generated text overlaps with reference texts, focusing on recall. The most common types include Rouge N, which looks at n-gram overlap, and Rouge L, which measures the longest common subsequence between generated and reference texts. In our work, we use the average Rouge L score to evaluate how well the model can reconstruct parts of a problem based on partial information, indicating its memorization ability. Lastly, we describe the exact match M metric, which checks if the model's output exactly matches the reference. If the generated output matches the ground truth, we score it as 1. Otherwise, it scores 0. We calculate the Rouge L score between the generated output and the reference, and if the Rouge L score is 1, we assign an EM score of 1. The final M score is the average across all test instances, with higher M values indicating a greater ability of the model to recall prompts accurately. Section Summary. In this section, we explore how reinforcement learning enhances the mathematical reasoning capabilities of the Quen 2.5 models, highlighting the importance of reward design and pre-training data in achieving effective performance. We also discuss our evaluation metrics for assessing memorization capability, including Rouge and exact match scores, to measure the model's ability to recall and reconstruct information accurately. Section: Answer Match Accuracy. In this section, we evaluate answer match accuracy by providing the model with a shortened version of each question, specifically the first 60%, and allowing it to generate a continuation without constraints. We then check if the generated response includes the correct answer, scoring it as correct if it does. Answer match accuracy is the proportion of prompts where the model's continuation contains the right answer. High accuracy suggests that the model can often retrieve the answer even from incomplete information, which may indicate data contamination. We utilize the Group Relative Policy Optimization (GRPO) as our reinforcement learning with value regression (RLVR) algorithm. For each question, GRPO samples a group of outputs from the previous policy and optimizes the model by maximizing a specific objective, where certain parameters are involved, and the advantage is calculated based on the relative rewards of outputs within each group. For our randomly generated arithmetic problems, the true answers often have high precision decimals. When the standard RLVR framework provides only binary feedback, the model rarely receives positive reinforcement, leading to unstable training. To improve this, we create a continuous reward system that ranges from 0 to 1, penalizing both absolute and relative errors between the model's output and the correct answer. In our reward design for RLVR experiments, we consider several types of rewards. A correct answer receives a score of 1, while incorrect answers get 0. A random reward gives a score of 1 with a certain probability. An inverted reward flips the correct signal, giving 0 for correct answers and 1 for incorrect ones. A majority vote incorrect reward only considers the majority voted incorrect labels, scoring 1 when the model matches an incorrect label. We replicate the performance of Qwen 2.5 Math 7b and Llama 3.1-8b instruct on the Math 500 benchmark with various reward configurations. The training accuracy curves show that random and majority vote incorrect rewards significantly improve accuracy for Qwen 2.5 Math 7b, but have little to no positive effect on Llama 3.1-8b instruct. When we apply the same RLVR method to Qwen 2.5 Math 7b instruct, the improvements are minimal compared to Qwen 2.5 Math 7b, indicating different sensitivities to RLVR between the two Qwen variants. Since the base and instruct versions of Qwen are trained differently, with the base model lacking exposure to dialogue-specific templates, we measure performance under 4 decoding configurations to get a fair estimate of each model's starting point. We find that using the official chat template significantly reduces performance for the Qwen base model, regardless of the sampling method used. We report 2 additional reference baselines, one representing the best performance of the initial model without a template, and another serving as a plausible upper bound on the model's initial performance. The apparent RL gains of Qwen Math 7b mainly reflect adaptation to the template format rather than true mathematical generalization. However, spurious rewards like random and majority vote incorrect still enhance the accuracy of the Qwen base model and maintain the performance of the Qwen instruct model, while ultimately degrading Llama instruct. This is a point we will explore further in the following sections. Section Summary. In this section, we evaluate answer match accuracy by assessing how often our model generates the correct answer from a truncated prompt, indicating potential data contamination if accuracy is high. We also implement the GRPO algorithm for reinforcement learning, design a continuous reward function to stabilize training, and analyze the differential impacts of various reward configurations on the performance of different model variants, revealing that spurious rewards can enhance accuracy for some models while degrading it for others. Section: Analysis of Memorization Capability Results. In this section, we analyze the memorization capabilities of the Qwen series. We believe that the differences in performance between Qwen and Llama may stem from the Math 500 evaluation set being unintentionally influenced by the extensive training data used for Qwen. To test this idea, we examine memorization across several well-known mathematical reasoning benchmarks. Specifically, we shorten the original questions to 40%, 60%, and 80% of their lengths and use these shortened prompts with the model. We then assess how well the model completes these prompts by calculating scores that compare its outputs to the correct answers. Our findings, detailed in a table, show clear signs of data contamination in the QUEN 2.5 models when tested on benchmarks like Math 500, AMC, and AMY 2024. For example, when we provide just the first 60% of the questions, QUEN 2.5 Math 7b can accurately complete over half of the remaining problems on Math 500, achieving a completion rate of 54.6%. Even with only 40% of the questions, it still recovers 39.2% of the unseen problems. Similar trends are noted for AMC and AMY 2024. These results suggest that the benchmarks for QUEN 2.5 may be affected by data contamination. While training on large web-scale datasets enhances mathematical reasoning capabilities, it also includes publicly available benchmark problems, which can skew results on older benchmarks. Removing these instances during data collection is quite challenging. We also summarize the accuracy of the model's answers based on different amounts of input questions. The results, shown in a figure, indicate that even with partial questions, QUEN 2.5 models achieve high accuracy on Math 500. For instance, with 80% of the questions, QUEN 2.5 Math 7b reaches an accuracy of 63.8%, and even with just 40%, it still achieves 41.2% accuracy. Since our evaluation only checks the final numeric answer, the model can sometimes provide the correct answer by chance, even if its reasoning is flawed. This explains the unexpected performance increase seen with Llama on AMY 2025 when only 40% of the questions are given. Among the correctly solved questions, the model's responses often include coherent reasoning and valid Python code, although this code is not executed. We present several examples to illustrate this. The presence of such structured solutions suggests that the training data may have included publicly available resources with detailed solutions to benchmark problems. Consequently, the sudden performance increase observed under random rewards is likely due to the model retrieving memorized answers from its training data, rather than reflecting its reasoning abilities. To further support our hypothesis that the unusual performance increase of QUEN 2.5 Math 7b on Math 500 is mainly due to data contamination, we replicate our experiment using a newly created dataset that the model has not encountered before. We believe that for math problems free from contamination, the model's reasoning ability still needs properly aligned reward signals to show meaningful improvements. For the random calculation dataset, we use an algorithm to create a set of mathematically challenging yet verifiable computation problems. These problems consist of expressions made from basic numerical elements, including integers from 0 to 100, fractions, squares, and cubes. We randomly generate mathematical expressions with 1 to 20 steps, using the 4 basic arithmetic operations: addition, subtraction, multiplication, and division. Each generated expression is paired with a standardized problem prefix, resulting in 20 sub-datasets, each containing 1,000 unique problems. We refer to this collection as random calculation, and examples from these datasets are provided in a figure. Section Summary. In this section, we analyze the memorization capabilities of the QUEN series models, particularly focusing on the potential data contamination in their training data that affects their performance on mathematical reasoning benchmarks like Math 500. Our experiments reveal that QUEN 2.5 models can reconstruct a significant portion of unseen problems even with partial prompts, indicating that their high accuracy may stem from memorized answers rather than genuine reasoning ability, prompting us to create a new uncontaminated dataset, random calculation, to better assess their true mathematical reasoning skills. Section: QUEN 2.5 Feet-S Initial Performance on Random Calculation. In this section, we examine the initial performance of the QUEN 2.5 models on the random calculation dataset. We first assess their zero-shot performance, noting that when we use chat templates, the models struggle with mathematical reasoning as the number of computation steps increases, indicating a need for improvement in multi-step calculations. However, when we remove the chat templates, the models perform best on problems with 3 computation steps, but their performance declines afterward. Next, we conduct RLVR training on the Quen 2.5 Math 7b model using the random calculation datasets to help the model generate answers that are as accurate as possible. We set up experiments with 2 datasets featuring 5-step and 10-step calculation problems, each containing 1,000 problems, 700 for training and 300 for validation. Our training results show that when we provide correct rewards, the model's performance improves steadily. In contrast, using random or incorrect rewards leads to unstable training, and with inverted rewards, the model's performance drops quickly. This suggests that only correct reward signals can effectively guide the model in improving its reasoning on problems not seen during pre-training. We also evaluate Llama 3.1-8b instruct and find similar results. Only accurate rewards lead to consistent performance improvements. We note that achieving a reward of 1 on a random calculation instance is nearly impossible, so we report the highest score among 16 samples, max at 1.6, instead of pass at 1.6. We find that Quen 2.5 Math 7b can exceed the max at 1.6 threshold with correct rewards, indicating that reward-aligned RLVR successfully transfers the model's strong single-step arithmetic skills to more complex multi-step calculations. However, with incorrect or random rewards, the model's performance either remains the same or shows only slight, unstable improvements. This emphasizes the importance of correct reward signals in enhancing performance on clean datasets. Interestingly, Llama 3.1-8b instruct does not surpass the max at 1.6 threshold even with correct rewards and performs worse than the greedy decoding baseline with misleading signals. This suggests that Quen 2.5 has stronger mathematical abilities than Llama 3.1, but this strength does not explain its performance boost under misleading rewards on contaminated datasets. Due to our limited computational resources, we focused our experiments on a subset of the Quen 2.5 models. We plan to include the Quen 3 series in future evaluations, as it may still face similar challenges. Many new reinforcement learning algorithms have been proposed to improve mathematical reasoning, but it is not feasible to evaluate all of them comprehensively in the near term. In our future work, we will systematically assess a wider range of benchmarks, reinforcement learning methods, and model families. Additionally, we will conduct a thorough theoretical investigation into the unexpected behaviors we observed, aiming to understand their root causes and improve our grasp of the underlying mechanisms.